Hello, Mr. Ryan, right? Okay, so can anybody tell me what's the binary search tree, please?
In the tree where left is smaller than root, right is bigger than root.
Okay.
And Chesley is near the door.
Okay, that's fine. Let's say the left is smaller, strictly smaller, right? Okay, so I'm going to show you a tree, and then you can tell me that if it's a binary search tree, okay?
I don't think so.
Why?
No, because 7, 8
yeah.
is small. Is 8 is bigger than 7 and it's to the
Well
left.
done.
Everything has
Yeah,
to
but-
be like everything to the left is smaller.
Yeah, everything left is smaller. So this 8 is clearly bigger than 7. So this is not a binary search tree, okay? So can you tell me what's a pre-order, in-order, post-order? Remember?
Is a method of like order on using
Yeah,
depth search and depth search. I think breadth search uses like pre-order.
For
In
order, if you use in order on binary search tree, then it'll be like in
Getting an order, okay. So, okay, that's good. The pre-order, so let's say in order, right? If this is the binary search tree, like 6, this is the binary search tree, then in order, so what's in order? We visit
it'll
the
be
left
roots.
to right. Okay, so
Yeah.
basically it'll be 4, 5, 6, 7, 8. So in other words, if we given a sequence like 4, 5, 6, 7, 8, and 7, 9, if I tell you this is the in order of binary search tree, you can tell me yes, it is, right? Because this is sorted, it's easy to check, right? Yeah. This is trivial. But for pre-order and post-order, you'll be more challenges. Okay, so let's say if I tell you 7, 5, 4, 6, 9. Is this a pre-order of a binary search tree? Without, I'm going to cover this. So I'm going to cover this. And then can you tell me if this is the pre-order of a binary search tree?
I think so.
You think so?
I think so. Maybe.
Wait, what's pre-order? Is it root left?
Yeah. So pre-order, right? 1, this is 0, this is 2. So pre-order would be 1, 0, 2. So the root. So basically root, left, right.
So that's
No, the left, right. Okay.
So that's.
Pre. What's pre? Because this thing comes in the first. So let's pre.
So is it post
Yeah.
order? So is that post order? Is that post order?
No. Okay, listen. So I'm telling you this sequence.
I don't think so.
You don't think so?
Might be.
Why? Why? Well, okay, tell me why it's nothing so. Why is it nothing so?
Because like this one's for your root, yeah, and then that's left,
Yeah.
and that's right. The right can't be smaller than left.
Right can't be smaller, right? But this could be the left as well, right?
I know, but like,
Okay, so look at this. What's the pre-order of this?
oh, I see it now.
Yeah. So 7. Okay, and then now 5, and then the 4, and then the 6, and then 9.
Then
Right?
what-
This is perfectly fine for a pre-order,
then
right?
what's 7, 5, 6, 4, 9?
7, 5.
6, 4, 9.
Then okay, so if I tell you 7, 5, 6, 4, 9, then that's definitely not a pre-order of a binary
Well,
search
not
tree. Why? Okay, so this is the question today. I give you a sequence, and then can you tell me if it's valid for a pre-order for a binary search tree?
Well, it's not pre-order, but it's definitely not post-order since post-order is like right, left.
Yeah,
And right is 9, not 5.
we worry about post-order later, but today this is just a question of pre-order. And as we said, if it's an in-order, it's trivial, right? It's simple. You just check if it's it's increasing sorted, right? That makes sense?
Okay.
But this is pre-order thing. Okay. So any thoughts? I give you this and you tell me it's fine. It's fine. So what happened? Okay, so this might look hard at the beginning, but I give you 2 hints.
Use a rubber.
Use a rubber. Okay, thank you. So what happened if these numbers are decreasing? What happened?
Then
Yeah,
that is
just
going
be
to
like-
the left.
Yeah.
You always go left. That's good, right? If it's a strictly decreasing, right? 7, 6, 5, 4, 3. If it's strictly decreasing, then we can just put it on the left because it's always valid. The left is smaller, right? Then what happened if, like, for example, like this number, right? If this next number is bigger than 4. Okay, so let's say, look, 7, 4, 7, 5, 4. Okay. now I tell you the next number is 6. Why is it here, not here? You know,
Because it's bigger than 5.
right? Look, you know, if it's bigger than the previous, it must be on the right tree, right?
Yeah,
Make
but
sense?
it's
Does it
still-
make sense?
But it's still smaller than 7.
Okay, that's good. Okay, so now 6 is bigger than 4, right? So it must be on the right. So why not here? Why not here?
Because that
It's
is
smaller.
Yes.
going to be smaller
Okay.
than 5, but
That's good.
it's larger than 5.
In other words, we can't put it here because this violates that. We are on the left tree. The 6 must be bigger than that. Okay, so if I tell you, okay, now, right? You know, if it's on the left tree, I can just put it on the stack, right? I have a 6. I can't put it there, right? I can't put it there because I want to maintain a structure here. This is strictly decreasing in a stack. So I need to take this out. I need to take it out until it's smaller than, right? This 6 is bigger than 4, so I take it out. 6 is bigger than 5, I take it out.
6.
Now 6 is smaller than 7, right? Why? Because 6 would be smaller than 7, right? So I can put it on the left of the 7, right? I can put it on the 4, that's fine. I can also put it on the 5. Make a decision, right? If I this new root 6, I can put it on the 4. I can also put it on the 5. So which number I should put it on? Because I want to trace back to the furthest root, so I can put it on the left of the root.
Yes.
Because if I put it on the previous root 5, if put it on here, then that will violate this, right? Does it make sense? Or even here, right? Yeah, make sense?
Just me.
Eric, you seemed a little bit confused, or did I explain it correctly? Okay, so one thing is that so rule number one, if it's decreasing, if it's the next number is still decreasing, that is fine. We can just keep putting on the left hand side, right? Because it stands the binary search tree. The left nodes are strictly smaller. Smaller number, we just keep putting on the left hand side.
Yes.
If it comes with a bigger number, then we can't put it on the left hand side, right? So we need to check where do we put it. It must be on the right hand side of some node, right? The thing is that we need to go as far as possible to the top, right? Look at this 6 example. We can put it on the 4. We can also put it on the 5. Okay? So if we can put it on the 5, we can't put it on the 4. Make sense? If we put it on the 4, then
That's more than
yeah. So we need to trace back, right? Can we put it on the 7?
Yeah.
No, right? Because 6 is smaller than 7. Okay, so this is the place that it finally lives. Make sense? So how do we do it? We use the stack. This is called the monotonous decreasing stack.
autonomous or something.
But yeah, something like
That
that.
sounds very
So
good stuff.
what does it mean? It means the stack, right? Remember, the stack is first in, last out. But we want to keep, we want to make sure that the numbers on the stack are strictly decreasing. Look, 7, 4, 5, 4, okay? Yeah? Then we come with the number 6. So what happened? In order to maintain this characteristic that the stack is strictly decreasing, so we need to take this out, and then put a 6 here. Right? So the stack is decreasing
So
strictly.
why does it need to be?
Good question. Why? We want to maintain this. So next time we come another number. Next time we come another number, we can do the same thing, similar thing. We can just keep checking. Okay? So we put a 6 in, so we know the previous root is 5. Now we are currently at root 5. And then if we come another number, like let's say, what can the number be here? Smaller than 6, bigger than 5. That's 5.5, right? If it's smaller than 5, smaller than 6, we can keep doing that.
Okay, but like, what if you go on like, let's say, what if you like go on the right hand side of a tree, like 9? But 9 is bigger than 7.
Okay, so now 9. Let's say 9. Okay, we have
like
another 9.
dead.
Yeah.
I mean, like on the right hand side of the tree, it doesn't have to be 9, but like it's bigger than 7. Like, how do you put it on that side?
Put on. Okay, so look at 7. 9. Okay, so let's pick this number. Okay.
Yeah,
Okay.
yeah, I know.
Okay, 9. So what happened then? 9 is 9 smaller than this 5? No, right? Because we are currently, if it's smaller, then that's
I
bad.
know.
Yeah, okay. So 9 bigger than 6, bigger than 7. We take it out. Put it here. So because we are on the right tree, we don't care about the left tree anymore.
So how do you know like? So how do you know if like it doesn't work? Like
Well done. That's the second question. Yeah, well done. I am glad you raised this. How does know it doesn't work? It's not valid, right? We maintain this. So why is it not valid? How come it's not valid? If let's say, let's coming back to this, 7 and then 5, okay, and then 6, okay, and then 4, okay, 4 is smaller than 6. Then that's not valid. Why? Because we are currently possessing these do the 6 here, and then you tell I'm on the right hand side 3, and you tell me we have a 4 here, and that's not right.
how are you supposed to know there's no 5 in the stack?
No, the root is now 6.
I know, but how are you supposed to know it's not valid? Like
If the current sequence pre-order,
I
remember?
know, I can see that, but you can't see on the stack. 4 is supposedly has to be like bigger than 5. It's not, but I can't see that on the stack. Like there isn't any 5 on stack. So how am I supposed to know by looking at the stack?
There's another variable called previous root. Previous root. Of course, it's not a step. Previous root. Previous root. Okay. So when you pop it out, when we're going back to the top, when we pop it out, we update the previous root. So it means that we are on the right hand side of that root, and then you tell me a value which is smaller than the previous root
Yeah,
here, then it's invalid. Does it make sense now?
Yeah, I know.
Okay.
I know.
Good. I'm glad you understand. Okay.
Yeah. Okay.
Any more questions about this?
No.
Okay. So I'm gonna write it. Okay. It's very simple code. Okay. This is called monotonous decreasing stack. Okay. Given I define, let's say is valid pre-order a binary tree, right? BST, and given a sequence ARR, and return a boolean. Okay, so of course we need a stack. We use a list. And the previous root, PR equal at the beginning none, right? And then we just iterate from left to the right for the ARR. For I in ARR. This is Python. Anyway, you pick this GCSE, right? You go to write this. This is simple, right?
What?
This is Python. You know that, right?
I know.
Teacher. Yeah, okay, good. Just make sure we're on the same page, okay?
Yeah.
For I in AR, right? So if the previous root is none, is not none, right? If previous root is not none, and if this I is smaller than the previous root, then this is the invalid case, return false, right? Right? Remember this 5, and then I'm on the right hand side, and you tell me, okay, there's a 4. This is clearly not right, okay? Then return false.
When do you change my previous root?
Well done. I'm going to write it. I haven't reached that bit yet. Then look, this is a stack, right? Why stack is not empty, and the current number is I, right? Is bigger than the stack, the top of the stack. Then we do this. We do the previous root. We update the previous root s.pop, right? And then that's it. I think that's it. And then after that, we need to push this to the stack, and then return true if we don't find a violation, right? So
I don't get it.
which one you don't get it?
That the last.
This one, these two. This is after the previous root. This look, this one, right? What's the tree again?
No, I mean like I don't get it.
7, 5, 4. Is it 7? No, 7, 5, 4. What's the other?
7, 5, 6, 4 was an invalid one.
No. 7. What's that? 7, 5, 4, 6,
9.
9. What's the pre-order of this one?
7,
5, 4, 6, 9. Okay? And I'm gonna have a stack. Okay? At the beginning, previous root is none. Okay, it's none. Okay? It's none. Okay? 7. This is none, so we don't execute. And this is none. The stack is empty, so we don't execute. And then we push the 7 here. 5, right? Previous root is still none.
But,
The stack is not
but
empty.
7 is a root.
Yes, but it's previous root. We said previous root. This is current root.
Yeah, so let's say the next one was 9.
So the next one was 9.
So no, let's say the tree was like 7, 9, like it was only like right hand side. But like
Like that.
yeah.
Okay? Okay, let's do it. 7, right?
Yeah.
And then we push it here, right? The second one, 9. Okay?
Yeah.
So what happened there? If previous root is still none, the stack, okay? 9. 9 is bigger than 7.
Yeah.
We take it out. The previous root now is 7. Now I put a 9 here. The end. It doesn't violate here. The end.
So I don't get those stuff.
This stuff.
All of that stuff.
This one.
Everything to do with previous root, like
Okay, yeah, okay, now I have another one. Say,
8.
no, not 8. 8,
7.5.
6, okay. This is invalid, right?
Yeah.
Okay, now 6. 6. Previous root is 9, is 7. 6 is smaller than previous root. 6 is smaller than previous root.
Okay.
False. Because we are on the right hand side. Everything should be bigger than previous root. Now you give me a smaller one. Perfect. Invalid.
So what's the other stuff?
What's the other stuff? This one.
Like the
left
while,
side.
yeah.
This is just okay. So now I have let's say I have this, right? I have here, say 8.9. This is valid, right?
Okay.
8.8,
Okay.
8.7.
Okay.
So, right, this number 8.7, 8.8, 8.9 is still bigger than PR, so it doesn't get executed here, right? But
Yeah.
it's the previous stuff. But the stack is empty, and this number is not bigger than that. So it doesn't get it doesn't pop it. So it's still. So I will still put it here. So it will still put it 8.9, 8.8, 8.7. Okay.
Yeah.
Yeah. Makes sense.
Yeah.
So why? Because every time you give me a small number, I can always put it in a queue. This is for tracing the root. Remember that first example, right? We want to find a number. We want to trace back to where to put the right tree, right node, right? If it's bigger, then I need to trace back. To see where I put it. Make sense? Yeah.
Yes.
Monotonous, right? If it comes with a small number, I can put it on the left hand because the binary search tree. Rule number 2, if you give me a bigger number, I need to trace back to see where I put it. Rule number 3, here, right? If we are on the right hand side, and then you give me a number which is smaller than the root, then it's invalid. Does it make sense?
Yeah.
Okay, any more questions? Don't worry, this is a hard question. I mean, it's a medium in decode, but at your age, I think it's a hard question. But this is logic. Okay, this is logic. Just like checking if a sequence is a valid in order. You tell me, oh yeah, we just check if it's sorted, right? Because yeah, it is sorted, right? If it after the binary search tree. Okay. Any questions, Eric? Okay, that's it for today. Bye bye.
Bye.
Bye bye.
Bye.